Hello, my name is Cristhian Salas from Tech, and today I wanted to talk about my project, which was Seismic Body Wave Attenuation and Differential Travel Time Maps of Alaska. This project wanted to elucidate the attenuation and velocity patterns of this area, and this is because Alaska is one of the most seismically active places of the world. The deployment of the Transportable Array to Alaska and Western Canada represents an important opportunity to study and understand better this place. This array is also known as AKTA. It is also important to introduce the concept of attenuation, which is a frequency-dependent factor that can affect the seismic amplitude during wave propagation. We can have different types of contributions, but in this case we're going to focus only on intrinsic attenuation, which means the conversion of seismic energy to heat. In order to carry out this study, we use 1,022 seismic stations. We use the information of 857 earthquakes. And as we can see in Figure 1, we have all the stations plotted within the studied area. We have all the earthquakes, the teleseismic earthquakes that we use for this study, and they were all the events with a magnitude between 6 and 8 that occurred between January of 2013 and July of 2019. Regarding the methodology, we calculate differential travel time and differential attenuation for P, S, and SKS arrivals. In the case of the differential travel time, we use a cross-correlation method as shown in Figure 3, where we plot all the traces for a single earthquake by the distance to the epicenter of the earthquake, and we choose a window. We clean and filter this window, and finally we cross-correlate them. So in this way, we can calculate the different arrival times for the different phases. In the case of the differential attenuation, we use a spectral ratio approach, where we calculate the spectrum of the signals, we calculate the spectrum of the noise, we compare both of them, and then we determine the frequency at which the spectrum of the signal was higher than the spectrum of the noise. In this case, we have the window for the noises, the window for the signals, and the way how this works is we compare every single spectrum to all the spectrums of the stations that were in a radius of 5 kilometers. By solving a least square problem, we calculate the station average for both methods, and this is how we get the following maps. These are our results. These are the maps for the differential travel time for P arrival, and this is for S and SKS arrivals combined. Here we don't have color scale, but blue represents fast arrivals, red represents slow arrivals, and here we can see that pretty much we have almost the same pattern. In the case of attenuation, blue represents low attenuation, less attenuation, and red represents more attenuation. So again, we have the map for the P arrival, for the S and SKS arrival, and here we can observe pretty much again the same arrivals, the same patterns, I'm sorry. And then here we have a smoothed version of this map. This is a smoothed version of this map. And we can interpret the difference between the different methods and also the different arrivals in terms of the different sensitivity that attenuation has for the temperature variation. So attenuation is more sensitive than velocity to temperature variations. And we have different particle motions for the different arrivals. So we interpret this difference in terms of these factors. Then we have the tomography information, and in this case, if it's true that the station average gives us an important large-scale geophysical structural information of this place, we also wanted to know what is happening at the subsurface, and this is why we invert all of these results for tomographic models. In this case, we invert the differential travel time results for this tomographic model, and here we can see a depth slide 120 kilometers. Blue represents fast velocity, red represents slow velocities, and here we have a cross section from C to D. Here we can clearly see how the slab is going down, and we need to keep working on these models because they are only preliminary results. In conclusion, I can say that we can combine these two methods in order to get a better constraining of what is happening at the subsurface. And then we can also interpret these results in terms of the slab that is being subducted. Thank you very much.